Solving a system of equations usually means Gaussian elimination, hours of row reduction. But for a special class of bases, finding the answer takes no work at all. Just one multiplication per coefficient. The same idea gave Fourier the formula behind every MP3, JPEG, and signal processor on Earth. On the left, x sub 1 equals q sub 1 transpose times v. On the right, a sub 1 equals 1 over pi times the integral from 0 to 2 pi of f of x times cosine x dx. These are the same equation. Let's start with the vector case. A basis is a set of vectors, q1 through qn, that lets us write any vector v as a unique combination. V equals s1 times q1 plus x2 times q2, all the way to xn times qn. The numbers x1 through xn are the coordinates of v in this basis. Finding them usually means solving a linear system, but here's the question: can we get x1 directly without touching the others? With a generic basis, no. With an orthonormal basis, yes. And the trick is one of the most elegant moves in linear algebra. Orthonormal means two things at once. Each vector q sub I has length 1, and any two different q's are perpendicular. Compactly, q sub I transpose times q sub j equals 1 when I equals j, and a 0 otherwise. The transpose turns a column vector into a row, so q sub I transposed times q sub j is just the dot product. Now watch the trick. Take the equation v equals x sub 1 times q sub 1 plus x sub 2 times q sub 2 and so on. Hit both sides with q sub 1 transposed. On the right, we get x sub 1 times the quantity q sub 1 transposed q sub 1 plus x sub 2 times q sub 1 transposed q sub 2 plus more terms. Every cross term, q sub 1 transposed q sub j with j not equal to 1 vanishes to 0, and q sub 1 transposed q sub 1 equals 1. So the entire right side collapses down to just x sub 1. The result, x sub 1 equals q sub 1 transpose times v. Now let's stack those q vectors as the columns of a matrix q, then v equals q times x, and we want to solve for x. From the previous frame, each coordinate is x sub k equals q sub k transpose times v. Packaging all those together, this means x equals q transpose times v. Compare this to the usual answer, x equals q inverse times v. Putting them side by side, we see that q inverse equals q transpose. Inverting a matrix simply by transposing it, that is the magic of orthonormal columns. One important caveat: this identity needs q to be square. The product q transpose times q always equals the identity when the columns are orthonormal, because entry ij is q sub I transpose times q sub j, which is 1 on the diagonal and the 0 off the diagonal. But q times q transpose equals the identity only when q is square. For q inverse to equal q transpose, we need both products to land on the identity, and that forces q to be square. Now here's where it gets beautiful. What if our basis vectors weren't vectors at all? A vector space only needs two operations, addition and scalar multiplication. Functions have both. You can add f plus g, and you can scale a function by a constant. So functions form a vector space, an infinite dimensional one. Fourier proposed a basis built from familiar pieces. The constant function 1, then cosine of x, sine of x, cosine of 2x, sin of 2x, and so on, forever. Any reasonable 2 pi periodic function, meaning a function that repeats every 2 pi, should be expressible as a combination of these basis functions. So the expansion looks like f of x equals a0 plus a1 cosine x plus b1 sine x plus a2 cosine 2x plus b2 sin 2x and onward. The question now becomes, how do we find the coefficients? We need an inner product for functions. Recall that the vector dot product is a sum. v dot w equals the sum of v sub I times w sub I. To adapt these two functions, we replace the sum with an integral. Define the inner product of f and g as the integral from 0 to 2 pi of f of x times g of x dx. The idea is the same. Multiply pointwise, then accumulate over the domain. Let's check orthogonality on a concrete pair. Consider the integral from 0 to 2 pi of sine x times cosine x dx. Using the double angle identity, sine x times cosine x equals 1/2 sine of 2x. The integral of sine of 2x over a full period is 0. The positive and negative lobes cancel exactly. So sine and cosine are orthogonal on this interval. Let's apply the same trick again. Suppose f of x can be written as a 0 plus a 1 times cosine x plus b 1 times sine x plus a 2 times cosine 2x and so on. To extract the coefficient of 1, we multiply both sides by cosine x and integrate from 0 to 2 pi. The left side becomes the integral from 0 to 2 pi of f of x times cosine x dx. On the right side, distributing the integral gives a 0 times the integral of cosine s plus a 1 times the integral of cosine squared x plus b, 1 times the integral of sine s times cosine x plus a 2 times the integral of cosine s times cosine 2x and so on. Now watch what happens. Every cross term vanishes by orthogonality. The integral of cosine x alone over a full period is 0. The integral of sine x times cosine x is 0, as we just computed. Cosine x against cosine 2x is also 0. Only one term survives, a 1 times the integral of cosine squared x. Now let's compute the surviving integral. Using the identity cosine squared, x equals 1/2 plus 1/2 cosine of 2x. Integrating from 0 to 2 pi, the first half gives 1/2 times 2 pi, which is pi. The cosine 2x part integrates to 0 over a full period. So the integral of cosine squared x from 0 to 2 pi equals pi. Our equation now reads, the integral of f of x times cosine x equals a1 times pi. Solving for a1, we get a1 equals 1 over pi times the integral from 0 to 2 pi of f of x cosine x dx. There it is, the Fourier coefficient formula. Compare this to x1 equals q1 transpose times v. Same structure, take the inner product with the basis function, then divide by its norm squared. Let's talk about that 1 over pi prefactor. The Fourier basis is orthogonal, but it isn't orthonormal. The norm squared of cosine of s is pi, not 1. If we rescaled each basis function by 1 over the square root of pi, we get a true orthonormal basis, and the formula would lose its prefactor entirely. So the 1 over pi is exactly the normalization fix. Now let's lay the two worlds side by side. In the world of vectors, the basis is q1 through qn, the inner product is a sum, and the coefficient is xk equals qk transpose times v. In the world of functions, the basis is 1. Cosine of kx and the sine of kx. The inner product is an integral, and the coefficient is a k equals 1 over pi times the integral of f times cosine of kx. Notice we did exactly the same thing twice. That's not a coincidence. That's the entire point. One more piece. The constant term, a naught, is simply the average value of f over a period, the projection of f onto the constant function. And each Fourier coefficient is just the projection of f onto a single mode. Add enough modes together and a square wave emerges from smooth sinusoids. This is the engine behind signal processing, image compression, the solutions to the heat and wave equations, and the quantum states written as superpositions. Whenever you decompose something into modes, you're using an orthonormal basis and the inner product trick. Linear algebra didn't just generalize to functions, it became analysis. One single formula, projection onto an orthonormal basis, runs through finite sums, infinite series, and the continuous spectra of the physical world.